Right. So I'm Sam Procter. I'm an architecture researcher. I work closely with Peter Filer, who is the PI on this work. We're jointly PIing a project that actually spun out of this that looks at both security, which this talk is about, and safety, which of course is closely related. So the upshot of this whole work is that we already have critical systems built that are exposed to security threats. That's just a fact of life. And it doesn't matter what that critical system is, whether that's some sort of plane or avionics software or a medical device or something else. Increasingly, these devices are connected, and so then they are exposed to security threats. Also, we find that increasingly there is model-based engineering being done in these domains. So a lot of times, of course, we say you should be using AADL, but really model-based engineering is increasingly ubiquitous in these areas where extremely high-quality software is necessary. So this project is all about looking at the payoffs of combining this model-based engineering and some type of security analysis. So what we found is that there are significant payoffs to be gained by looking at architecture-level security in addition to code-level security. So we're going to talk a lot about the avionics industry, partially because it's embraced this model-based architecture-centric virtual integration for safety already. And so they've been a good sort of exemplar of what we can do with this type of information. Ultimately, there are three things that came out of this work, and that is the first, that you can analyze what we call security policy specifications for vulnerabilities. Then you can ensure that those policies are enforceable given the architecture that you've specified. And finally, you can generate a runtime system configuration from these verified models that is guaranteed to make sure that enforcement actually occurs. So let's sort of dive in. We already have in modern critical systems a pretty significant partition creating those systems from the outside. At least in a lot of cases, you have a pretty strong firewall, things like that. So you can't just walk up to most critical systems and damage them. But there's not always the best protection between a system's components. A lot of times you see this in sort of the safety world. If a computer catches fire or if there's a problem in one compartment, in a well-designed system, there are going to be firewalls that block those sort of internal problems from spreading. So we wanted to look at if we could use similar techniques in the security world to achieve fault isolation even for security problems. Because if you track the details of many modern security challenges, what happens is a problem in one part of the system is exploited, which gains the attacker access to the entire system. And it's that second step that we really want to slow down. So like I mentioned, avionics is a good example of the situation here. Of course, a long time ago, right, planes had no communication with the outside world, maybe just a radio. But now planes are very heavily connected. And yet there's still quite a bit of confidence in both military and civilian avionics. I think automotive is a less positive example. You may have heard of the case where a reporter was driving a Jeep and some people were able to take control of that Jeep and drive it off the road despite not being in the vehicle. And of course, this has safety implications, this has massive cost implications, and consumer confidence, all sorts of problems. So really, the takeaway here is that it's more than secure code and external firewalls, that you really need some sort of security policy, and then you need to be confident in that policy's enforcement. So over the past several years, the SEI has developed the Architecture Analysis and Design Language, or AADL, which is an architecture modeling language that's now used all over the world. It's been standardized by SAE International, and here at the SEI, we play a big part in that standardization effort. So it's designed for embedded software systems, but really any critical system where it pays to have extremely high quality software, we think AADL is valuable. It includes support for all sorts of different analyses, things like timing, performance, safety, and then as a result of this work, various security analyses. So the extensions that we made in this project are numerous. Some of them are things like the security levels and domains that you may be familiar with, where you can say this is a high security part of your system or this is a low security part. You can specify that connections are encrypted, that various connections require authentication. You can also specify things like physical and logical exposure. So if you say, this part of my system unfortunately has to be used by users with no authentication or low authentication, so we expect there to be a lot of attacks coming from this, you can specify that and analyze your system accordingly. So let's take a little bit closer look at what exactly this project does to automate security policies and their enforcement. So in the beginning, in the first step, what you have is your functional mission system architecture, and you want to annotate that with the flows of information and the types of those information that you want to see moving through the system. So in effect, what you're doing here is you're building a whitelist. So you can see that we have 2 rows of components here. We have a high security in red and a low security in green. And so we have specified in our information flow that the red should go on the red path and the green should go on the green path. And so here, that's pretty straightforward. In a larger system, of course, that in itself may be a significant architectural effort. Then the second step is to verify that the hardware that you've specified can enforce those information flows. So now you can see in our new diagram here on the right that we still have green and red, but because AADL lets you bind the software elements, such as the threads and processes that are connected or that are communicating with one another, to specific pieces of hardware, we can verify that you're either not sharing hardware between high and low security, or if you are, then it can be flagged so that you know you need to use high security hardware that's capable of reliably separating different security domains. And then finally, you should be able to just click a button and generate these policies or code that will enforce these policies given a suitable architecture or a suitable secure operating system. I also want to point out that there's a really cool connection to research here where the Multiple Independent Layers of Security, or MILS project, came up with a bunch of theory in this area, primarily designed for confidentiality, and what we've done is we've moved that to integrity as part of this work. It's a really neat collaboration between us at the SEI and academia. So starting with our model and policy, we can begin by modeling the impact of potential impacts on our system. So this takes as a starting point the security policy and enforcement that we've checked on the previous slide. So now we have tools built as part of this project, like the attack impact analysis, that lets you say, what if one of my components that I mentioned had exposure to the world got compromised? And so then you can see a model of your system with that compromise. Because AADL knows the architecture of your system in addition to the various security threats, this turns out to be a fairly sophisticated analysis. You can also see things like, well, if I changed this connection so that it was encrypted, then this compromised component couldn't necessarily learn my secrets. So it really enables a very powerful what-if style of analysis. If you've worked in security, you may also be familiar with the attack tree analysis. This is a case where you have some top-level thing that you don't want to have happen, and you start to just sort of brainstorm about all the ways that that could occur. So, of course, this component could be compromised, or this connection could be taken out of service somehow. All of that combines in one way or another to your top-level problem that you want to avoid. But again, since this is architecture aware, because you've built your system model in AADL, there's really a big payoff here. And then finally, like I mentioned, you can generate the configuration files to actually enforce these security policies that you've specified. We've targeted a couple of certified kernels like SEL4, which has mathematically proven a number of desirable properties about it, and so you can have some fairly high level of confidence in your policies enforcement. So we recognize that these tools have to be used in the real world, and it's not enough to just analyze models as some part of an intellectual exercise. And so we believe that you should specify your security policy as verifiable requirements and then move those verifiable requirements or align those verifiable requirements to existing assurance requirements that are coming from some sort of regulatory body. So one of the papers that we've published on this effort talks about the workflow that you might follow when analyzing a system. Previous work on AADL has looked at formalizing verification activities. And so one of the cool aspects of this work is that we were able to leverage this previous effort called the ELISA workbench to take what are essentially security guidance, whether those are from the MILS project that I mentioned earlier or from the common weakness enumeration lists that are published, and move those into automatable verification plans. So what you can see on the right here is an example of the ELISA workbench, where the developer has taken the required verification activities or the suggested verification activities and encoded them into the workbench. And so now every time a change to the architecture is made, whether that's refining it so that it's more detailed or making a change in response to some sort of customer requirement change, you can rerun your assurance activities and see which ones still hold and which ones require updates. So let's take a look at the concrete outputs of this project and where you can get them. Like a lot of people in this session and at the SEI, we collaborate quite a bit with people in academia and all over the world. And so our tools are available publicly on GitHub. This includes the policy and enforcement verification stuff, the attack impact and attack tree analysis tools. And then we also have example models. So we have modeled the Jeep and the Prius security incidents that you may have heard about. There's an aircraft model and one that I think was mentioned earlier where the entertainment system at least potentially could get access to the CAN bus. And then the drone case study. We also, like I mentioned, work closely with the standardization efforts behind AADL. And so we have a proposal for a security annex to move the entire standard body in a way that's more security aware. We've published papers and a longer technical report on security analysis and how that fits into an overall assurance workflow. And then, like I mentioned, all of this work fed into a successful proposal for a 3-year project that looks at integrating safety and security in an architecture-aware way. So let's take a minute to just step back and sort of sum up. We started with a lot of the outputs of DARPA's HACMS program, which very successfully demonstrated the benefits of using AADL-based verification on an unmanned drone. We demonstrated the feasibility of improving the security assurance with this architecture modeling. So we said not only is it important to analyze your code for security vulnerabilities, but so too should you be analyzing your entire system architecture. Next, within the community, we're going to continue working with SAE International to move the security annex towards approval so that it's widely adopted like the rest of AADL. And then here at the SEI, like I mentioned, we're going to look at developing an integrated approach to safety and security, which is a hot research area the whole world over, and I think an area where the SEI stands to take a real position of leadership. So I think I have a little bit of time left. I'd be interested in hearing any questions that you have. Right here.
So you said you modeled the Jeep case, right? So this was 2015, I think
right.
It was done. It was a 2014 Jeep Cherokee.
So, yeah.
The people who did it were formerly at NSA, and they worked for a Chinese company after that, briefly, and then came back and worked for GM now.
So to be totally clear, this project was started by a guy named Julian DeLonge, who actually did that modeling. So Julian has,
model.
he did that model.
So I guess the question is, if you have that much model fidelity, and you have these exploratory capabilities, can you generate attacks and novel attacks as a result of the capability?
So to be really clear about the Jeep model, it is a model of the Jeep enough to sort of describe that attack pathway. I don't want to claim that we have an AADL model that would fully specify the Jeep Cherokee and let you discover those novel things. I think that if we were Jeep and we had that full model, then I would totally expect it to be possible to discover those novel attack paths. As I understand it, this example was just a model of the attack path that was used and described in the literature.
So I guess 2 questions. So if I were not Jeep, but I didn't like Jeep, and I got those models, I could use this to generate novel attack capabilities.
I think
right?
I would that would be my expectation. That the same way that if you get access to like all the design documents for a system, you are given some advantage. I would expect that to be the case here. I should also be clear, though, in the HACMS project, the way it worked was a red team was given 48 or 72 hours to attack a system. They couldn't do it. They couldn't find any vulnerabilities. We then turned over all the AADL, the specifications, the design documents, and they still had 48 to 72 hours and couldn't find any vulnerabilities. So the base argument is that with sufficiently sophisticated architecture modeling, you will design a system that is very resistant, even if the design documentation is compromised.
So I guess the last question is, what about automatic model construction from existing artifacts?
So that sort of round-trip engineering, to my knowledge, is not in the tool environment.
I mean, is that a thing we could ever get?
So your input would have to be as sophisticated or more sophisticated than AADL. Because AADL's value comes from the ability to put all sorts of information in it. So whatever you're generating that from would also have to be that detailed.
I give you a car.
It would be hard, right? I mean, you would need.
I know. I'm sure.
I mean, maybe, yeah. You would need, you would need all sorts of like scanners and things to read it. So I would say that's.
But if I had all of those scanners, was it anything that, I mean, if I have all the hardware required to do this?
I mean, I don't know that hardware exists. If you have it all, then sure, but I don't know that there's something that can look at like a computer or a piece of metal and be able to determine the various properties that you'd want to know about it, like its weight, cost, those sorts of things. I've been given the hook, by the way. I'd be happy to talk to you afterwards.
It was the computer attack on the vehicles that was of interest. It wasn't whether the metal bends faster.
Oh, so just given the network?
Yes, the network and the ECUs and all that.
I think potentially, yeah, that's totally possible. I don't think that's anything that we have now, but I'll talk to you.